In this session, we will discuss about the chapter 2, which is frequency response in AC circuit. So obviously frequency response only will be available in the AC circuit. DC, you will have just like a straight line. So from this chapter, you will achieve the course outcome 3, which is ability to construct Bode plot for various type of transfer function and analyze the frequency response. And it will relate to the program outcome it's stated there. So this is actually will be more on analysis. Okay, and you will have like a frequency response, Bode diagram and Bode plot. This will be covered from this lesson. So frequency response, you see here we will have like a sorry, here usually you can see that you will have like an input and then output. In time domain you will have like this xt, yt and ht. Okay, but in time domain we cannot see a lot of information like where is the noise, okay, at which frequency the noise actually starts and at which frequency you should amplify your signal, okay, and what is the bandwidth of the system. So a lot of things actually you cannot obtain to the time domain. So therefore usually we will change to frequency domain. As you stated here, you will have like a x omega, h omega and y omega. Okay, so the omega also sometimes it will written as a omega equals to 2 pi f. So whatever it is actually in the frequency domain. So to change the frequency domain later in the next chapters, you will see on using like a Laplace transform and then Fourier transform. In engineering mathematics also you study about that, changing from time domain to frequency domain. And why? Because in frequency domain the analysis could be done much more easier compared to the time domain, and you can observe a lot of information. Okay, it's like for example, let's say you have like a low pass filter, okay, where you want to create the cutoff frequency. So things like this actually can be studied. Specifically in this chapter, you will have the response, correct, the transfer function. You will sketch the transfer function, you will see the transfer function, and from the transfer function you can see whether this is actually like a low pass filter, high pass filter, okay, or band pass filter. The response, how does it look like? Okay, but we won't go to on ask you to check whether this is actually low pass filter, but can be done as well. But mainly you will learn on how to draw it based on the transfer function. Okay, so in time domain, what usually we will do the analysis in time domain is actually difficult, so therefore we change to frequency domain, either in f or omega or s Laplace. And once the problem solved, we will usually convert back to the time domain again. Okay, for example, let's say you have xt and ht, and for you to find the yt, it's actually difficult in terms of time domain. So what we will do, we will change all of them to frequency domain. After find the y omega or ys, we will get back the yt. So this usually happens in the frequency domain. So the transfer function, the main possible function is voltage gain, current gain. Voltage gain means output voltage over input voltage. Current gain means output current over input current, and transfer impedance V over I, and transfer admittance I output over V input. Okay, and in transfer function, okay, in transfer, you also will study in your Laplace transform, the chapter 3. The root of numerator, okay, the root of numerator, it's actually known as a 0, and then the root of denominator is actually known as the pole. Okay, so based on this transfer function, the upper part, okay, this is actually known as the numerator, and the bottom part is actually known as the denominator. So the root of them actually known as a 0 and poles. Okay. The next slide. So for example, let's say from the transfer function given here, it also can be written in Laplace like this. J omega is actually s. Okay, because sometimes question actually it's shown as sometimes in the omega. Okay. And usually what we will ask you to draw the frequency response. This is actually the main topic, but at the same time you should know where is your actually poles and zero. So here this equals to 0, so and this equals to another function is actually this part actually equals to 0. This will give like a -2, so one is actually 0, one more actually give 0. So here you see j omega plus 2 equals to 0, j omega is actually -2. Either you can write in s as well, s equals to 0, s equals to -2. So these are the zeros. And as for the poles, we can see that we have like a negative form. So this is actually the poles. Okay, we have 2 zeros and 1 pole from this transfer function. Okay, and then one more, as I told you, because in time domain it's actually difficult to analyze, what we will do, we will change the time domain circuit to frequency domain. Like for example, let's say in this case, compute the transfer function h omega of the circuit and also identify the magnitude and phase of h omega. So here the h omega, it should be because we are given as the input voltage and output voltage. So here we'll have like a voltage gain transfer function. Okay, voltage gain transfer function. And before we further dive into the how to get the transfer function, we will get the we will transform this capacitor, or if there is an inductor, to frequency domain. Like if it is C, it's actually 1 over j omega C, where it can be written as negative j omega C. Okay, and then if it is what is that, if it is L, okay, inductor, j omega L. Okay, so it will be written in that form. Okay, and V out, it can be written as Vs multiplied with the Xc divided by the total impedance available here, where Xc plus Xr is actually can be written like that. Okay, so Vs over V out over Vs is actually Xc over Xc plus X. So this is actually the transfer function. Okay, this will be the transfer function of this particular example I just explained, and now you have like a full derivation here. So V out is 1 over j omega c, where I write as a Xc there, Xc plus Xr, you see. So here the whole thing is actually given like that, and what we will do, we will eliminate, we won't keep the j omega c or s on top of the function. I mean the numerator, we will keep it like a 1. We won't keep it like a omega, the frequency part there. So we will multiply with j omega c to keep the j omega only at the denominator. So some minor modification will be done, and after you have this h omega transfer function in this form, it's easier for you to calculate what is that the magnitude and phase. The magnitude, actually, if you remember the basic math last time, if you have like a complex function like this, you're going to have like a 1 over square root of 1 plus omega rc square. Okay, and then the tangent is the phase is negative tangent, inverse tangent of omega rc. Okay, so this is what you will get, okay, usually from the magnitude and phase from a simple transfer function. Okay, and additionally what we will do, we will plot the magnitude and phase in this chapter particularly. So you should know what to get from the circuit, okay, what is supposed to get from the circuit, and what to draw, okay, based on the transfer function, how to draw it, okay, to represent the magnitude and phase. So we will go to one step higher, like from what you done before. So all this is actually important, how to calculate, how to get the transfer function. Even for the next chapter, we will apply regardless, that is a Laplace or Fourier transform. In general mathematics, usually you'll learn on how to deal with the mathematical parts on solving the Laplace equations. But in circuit, we will apply the Laplace and Fourier transform knowledge on solving the circuit. Okay, so we will go one step higher, and particularly in this chapter, we will go until the level of sketching the response in terms of magnitude and phase. This is another example. Okay, here you see for the given circuit, calculate the gain I, current gain, which is I output over II, and poles and zeros. Okay, we haven't go to the drawing yet, but it is given like that. So as I told you, what you have to do, you have to change the whole circuit to frequency domain. So frequency domain means the L you have to change to j omega L, and then the C actually you have to change to 1 over j omega C. So 1 over j omega C means 1 over j omega 0.5. So 1 over 0.5 will get like a 2 over j omega. And here you have like a 4 plus j omega L. So 4 plus j2 omega. Okay. So this and this actually in parallel. Therefore, using the current divider rule. Okay. I have a total current here. I need to take this branch over the total impedance where you have like a 4 plus j2 omega plus 2 over j omega. So and I you can bring it over here. So this is actually the transfer function asked from the question. But as I told you before, we won't keep the j omega on top of the numerator. Okay. So here the full solution where we try to it's not like we will eliminate. We will keep, if it is not 1 over j, sorry. So if it is in this form, we will keep it. If only if it is like a j like this, if you have like a 2 over j omega, then we will try to eliminate. Otherwise we can keep it, because that actually will give the poles and zeros one. Okay, so here okay, we have to up to this level in the previous question. So we won't keep the, as I told you, we won't keep the j omega at the denominator. So we'll multiply with 0.5 j omega here and top, bottom and top, to make it balance. Okay, so at last you'll have like this. Okay, and this equation you can factorize everything nicely. Finally you'll have equation like this. The factorized equation you will have like this, and also you factorize the equation, the quadratic part, you will have like a j omega plus 2, j omega plus 1, j omega plus 1. So you have like a, for the zeros, actually from here, root from here, you have j omega equals to 0, j omega equals to -2, j omega equals to -1. This is actually same repeated twice. So basically the idea is actually you start from here where you change the whole circuit to frequency domain. Okay, then you do like a normal circuit analysis to get the I naught, and I naught over I just bring the I here. After that you play around with your mathematics skill, because I don't want to have 1 over j omega here. So therefore I multiply with j omega, j 0.5 omega. So therefore the equation get like this. Okay, and after that you proceed with 0.5 multiply with 4 multiply with 2, you have this. Okay, and you just rearrange the equation, you just bring this one to front, nothing much there, and here you just factorize the equation. Okay, and finally you have like this, and from there you find the zeros and poles. The next thing, actually you can plot this on transfer function as well, and this is actually like a homework you can try later. Okay, to get the transfer function and then obtain the zeros and poles. Okay, you can try later, do by yourself. Okay, as I told you before this, we try to get the transfer function. If it is not given, if it is given, you will directly plot. And this magnitude and phase actually will be drawn in using the plot known as a Bode plot, and this is actually based on the logarithmic scales. So it's actually in decibel scale, you know. So we will convert that to 10 log. Okay, 10 log actually will give in the logarithm value. And like some additional knowledge I want to give here, this is actually gain, you know. Gain, it doesn't have any unit. But let's say you change power from decibel scale to from normal value to decibel value, okay, linear to decibel. So here you will have like a unit, okay. Power actually you have like unit dBm. You see m is actually milliwatt, okay. And to get the power in dB and 10 log PR, okay. But for gain, it's actually you will have like a P2 over P1, B2 over V1. So gain, it doesn't have any unit. The dB is actually not, you know, it's not a unit. It's just like a different form. It's actually decibel scale. To express decibel scale, we use the dB. dB is not a unit, okay. Just for you to understand better on this part, okay. So the scale actually will look like this, where you have like here you start from 1 and then 10 power of or 10 power of 1 and then 10 power of 2, 10 power of 3, 10 power of 4, something like that. So therefore you can have like 1, 10, 100,000. Okay, this is actually the scale here, and on top you will have here you could have like a, up to you whether you want to have like a 20 dB for 20, 40, 60 or 10. That's actually up to us. Actually we want to put here on the y-axis. X-axis you will have like this, okay. And so one problem with the transfer here is that it needs to cover a large range in frequency, and therefore you see like in x-axis you have this logarithm scale where you can actually you can cover a lot of frequencies, high frequencies within one single graph. So plotting the frequencies response semi-log plot, okay, where the x-axis form plotted in log form makes the task easier, okay. So these plots actually known as the Bode plots. Bode plots actually either you can draw the magnitude and phase, both actually can be drawn here. So we have seen like one example where how we change the magnitude, how you get the magnitude and phase from the transfer function, okay. But specifically for the Bode plot, we will use the log scale, okay. So main task we have to do is actually we need to change it to the standard form, okay. We have to change to standard form. So regardless how does your equation looks like, this actually looks very complex, but once you have your own equation, you know, you won't have all of these things. Maybe you have like a kj omega over this, or kj omega this and this, okay. Or you have like 1 2 3 and here, or 1 2 here, so up to the transfer function. But we will try to bring to the standard form like this. So the k is actually known as the gain value, okay. Maybe you have like a 220, something like that. This k is actually after you factorize everything nicely, where you have only one here, you see only one, okay, and here one, here is 2 because it's actually quadratic function. So everything just look like this. This z1 actually refer to the 0, okay. This actually refer to the 0, and this p is actually refer to the pole, okay, pole. So there are many things actually. Simple 0, simple pole, this is actually 0, this actually refer to direct 0, this is simple 0, okay. This could be on top or or bottom, the j omega. That's why we put like a plus minus 1. It could be on top. If it top means 0, at bottom means actually pole, okay. And this is actually we have for the quadratic, okay, quadratic pole, or quadratic 0 or quadratic pole, okay. Okay, like this. poles at origin, poles of zeros at origin, because we have a plus minus. This is real 0, this is quadratic 0, this is real pole, this is quadratic pole. Like for example, let's say you have given an equation like this. Okay, this is given equation like this, and from here we compare with the transfer function. So here the k is actually 2, z is actually 1, and then here the 0 is actually 2 as well, I think. No, 1 over something, actually we'll get like a 2, 1 over 0.5, something like that. So you'll have like a 1 over -2. Oh yeah, we have to change this one to what to call, because it's not in the standard form. We have to multiply with 2, so that you have like a 1 over j omega 2 over, you see I shouldn't have like a 2 here. I should have only 1 here. Okay, so therefore we will factorize the 2 out of the equation. Okay, and you compare with the what to call that, standard transfer function. I shouldn't have like a, and I shouldn't have like any number apart from 1 here. I should have like a 1 for the real pole. Okay, and therefore we have to refer to the the standard form, and then compare and try to modify the equation. Okay, so after the modification, you can see that this is after modification. This is actually before modification. After modification, you see that it's not modified, it's actually just compare with the general, the standard form. So k is 2, and the p is actually 1 over 2, as I told you here, after what to call, we modify the equation according to the standard form. So j omega over 2 plus 1, so over 2 is actually the p1. Okay, and here as well we have like a from what to call, from the quadratic pole and quadratic 0 here, the w n square. At this part we have like a, okay, wn square. What is that? This is actually 100, and this is actually 400, and 100 and 400 it will give you like a 10 and 20. Okay, so this is actually just we are getting what is that, the poles, and this need a lot of practice and observation, analyze, even for you to compare with your own equation, with the standard equation, and try to get the poles and zeros. So in a Bode plot, each of these factors actually plotted separately and added graphically, which means each of this, and if you have a like quadratic function, this, all of them actually will be drawn separately. After that, graphically it will be added. Okay, and what is gain, what is poles and zero, this is all actually maybe easier for you to see through the graph. So k will give like a straight line like this, gain magnitude constant. Okay, it's actually constant, so 20 log k is actually will give something like this, and the phase angle for constant is always 0. Okay, and the 0 at origin, okay, 0 at origin, it will give like a straight line like this. So at start from 1, you will have like a 20 dB scale. Okay, which means the, what is that, the gradient actually 20. Okay, 20 dB per scale, per dB per decade, sorry, 20 dB per decade. This is actually 1 decade, this is actually 1 decade. So per 1 decade you have like a 20 dB. For 1 decade you have like a 20 dB. That's actually the slope or the gradient. Okay, this is actually 0 at origin, and pole at origin you have the same thing, 20 dB, negative 20 dB decade, but in a negative side, and then your phase will be at negative 90. So we will draw one by one, but this just for your information. Okay, and this is actually real 0 on this side. Real 0, start from the 0 point that we got just now. Like just now we got like a 2, right? And for example, if you start from 2, you'll have like a 20 dB decay. Before that, actually 0. And as for the phase, you'll have like a z over 10. So 2 over 10, you will have start from the 0, and after 10 decade, after 1 decade, you have like it will start to have like a 90. So it will fluctuate within the 90, positive 90 to negative 90. Real means positive. Real poles means you'll have like a real 0 means positive, real 0 means you'll have like a negative. Okay, same start from here, and then you have like a 20 dB decay. Okay, so simple pole and simple 0, you get this one from the 1 plus something, right? 1 plus something. Okay, so this is also you can get from the equations such like this, but I don't want to refer to this exact and approximate table where you'll get confused. Okay, why they have like two things here, exact and approximate. We will look at the table later. And as for the quadratic 0, you will have 40 dB decay. Okay, 40 decay, and this will go until 180 degrees. Okay, and same for quadratic poles, you will have like a negative 40 dB decay. So the slope actually quite sharp, okay, compared to the real. Okay, so why you have like a 40? Because of the square. If you times it the 20, because we changed to 20 log, right? So you'll have like a 40. That's actually the reason for you to have like a quadratic pole 0 with 20. Okay, so this is actually the what in real you have like a slope for the what to call for magnitude and phase, but we no need to look at this level. We are just going to plot using this table. Okay, so here you see this is all actually summarize the how the line actually will be drawn both for magnitude and phase. So we will zoom them and check one by one. So k straight line, 0 phase, j omega n straight line, start from 120 dB per decade, positive 90. And for if it is a denominator, j omega n actually a denominator, you will have like a negative 20 and decade, phase actually at negative 90. And then you have like a simple 0 like this, means this z you have to will be starting point, and you'll have like a 20 dB decade. So this actually 2 means 2 to 20 2 means you will have like a 20, I think. Okay, at 20 you should have the gradient. The next point should be stop at grade 20. After that, state. No, sorry, not state. That's actually for the phase. And as for the phase, you'll divide by 10, and similar approach you'll use, but after multiply with 10 z, you have to stop and straight 90 degree. This is actually for the non-quadratic. Okay, and yeah, we have left one. So if it pole means negative 20, and it starts from negative 90. And as for the quadratic, from this expression we know the wn, right? So from the wn you will have like a 40 and 40 dB per decade. And as for the phase, you will go up to 180. Negative means at the denominator means negative 40, and will go until negative 180. Okay, so I think that's all for now, for you to grab the whole idea on what is frequency domain, how to convert to what to call the component, either capacitor or inductor, from frequency domain, time domain to frequency domain, and for you to get the transfer function from the simple circuit analysis. After get the transfer function, check with the standard form and predict how the body plot will be drawn. So now we are just actually go up to that level where we are just predicting how it will be drawn. And in the next session, we will practice on how to do it on the semi-log graph. So that's all. Thank you.